Hello everyone. In this video, I would like to share the answer to a very simple problem of a convolution in an LTI signal. So, this problem says that there is an input signal of that, and there is an input signal as well. And to determine whether or not it's stable, and to sketch the graph for the convolution. So, first of all, what even is signal? The signal is basically anything that changes as time passes on. So, for example, right now I am speaking, and the voice reaches its amplitude, and then it will decay. It will disappear slowly, and it can be considered a signal, specifically an acoustic signal. Another example would be our heart beating. We actually generate electrical voltages at a very small scale in microvolts. And those electrical voltages change after every heartbeat, and they are considered signals as well. They are specifically biological signals. So a system is basically anything that takes an input and then transform them into an output. Say like I am speaking into a microphone, and the microphone makes it louder on the speakers. And yeah, to find the convolution of this problem, I decided to divide the steps into four. The first step is to find the shape of the XT, the input. The second step is to find the time limiting function and the shape of the HT, which is the impulse response. The third step is to convolve one of them, and the last step is to find whether or not the system is stable or not. And I would like to also explain about input and impulse response. So the input is the main voice coming out of the person speaking or other stuff that is getting processed. Say like I am speaking right now, my voice is the main input, and HT is the impulse response. It will divide my voice into many different delta impulses, and delta impulse is like a spike of value at certain time periods. Basically, my voice, say like it's like this, like it's a wave, and after it is convolved with impulse response, it becomes like this: one, like those separated points. And the reason we do this is because we want to find the calculation for the output. We can actually find the calculation for the output in a harder method, that is with differential equations. But for an LTI system, we can skip all those harder calculations just with simply convolution with impulse response. However, we cannot do that with a non-LTI signal. So an LTI signal is a linear and time invariant signal, which means that if the signal is being moved, from one point to another, the output will also be moved as well. And if the signal is being enlarged or shrunk, the output will also change its shape proportionately. That is an LTI signal. It can be solved with, again, an impulse response. A non-LTI signal cannot be done so because the result of the differential equation will be different from the result of the impulse response. Okay. So now I would like to explain about how you can find the shape of the input signal. So now, first we will find the first step, which is the shape of the input signal. To do so, we need to first understand about what the input signal even is. So an input signal can be divided into two categories. The first one would be the signal envelope, and the second one would be the time limiting function. A signal envelope basically tells you how the signal strength will change according to time, whereas the time limiting function will tell you how long that signal will exist, from what time to until what time, the period of time where it exists. And as you can see, the signal envelope is minus 2t plus 4, whereas the time limiting function is ut subtracted by ut minus 2. Ut subtracted by ut minus 2 tells us that the signal exists between 0 seconds until 2 seconds, because it would be because according to the rule of time displacements, T is equal to 0 seconds, and for example, like T plus 2 means it is on negative 2 seconds. So yeah, to find the graph, we just have to input from 0 to 2, which is 0, 1, and 2, into the signal envelope. And the first one would be 4, which is here. The second one would be at 2, which is here. So at t equals 0 seconds, the strength of the signal is at 4. Whereas at t equals 1 second, the strength of the signal is equal to 2. And at t equals 2 seconds, the strength of the signal is 0. Therefore, the shape of the signal will be a triangle. So we have sketched the input signal. And I will check mark this to continue to the next step. So just now we have found the shape of the input signal. Now we are trying to find the shape of the impulse response. So as you can see in the input signal, it has a signal amplitude, which is minus 2t plus 4. And an impulse response doesn't have that. They only have time limiting function. But this one is no ordinary time limiting function. For example, in the input signal, you can directly tell that it starts from 0 seconds and ends at 2 seconds. For this one, there's no constant. There's no constant, meaning that it is infinite. So, like if you just write you can easily tell it is from 0 until 3, and it is from 0 until minus 4. And that is easy to tell, but this one is a bit different. To find the actual time value from this time limiting function, we need to use the unit step function. Why unit step function specifically? Well, it's because this is u. U just means unit step function. So anytime in the signal there involves u just means unit step function. This is what we will use in case you cannot find it directly through the simple subtraction method. So unit step function says that the value of the signal is 1 when it is greater or equal to 0, and its strength will be 0 if it is lower than 0, if the time value is lower than 0. So in this function, we just have to fill the t with the value of certain scenarios, and we will pick 3 scenarios. The first one is at t less than 0, the second one is at t equals 0, and the third one is at 3 greater than 0. Why specifically below 0, at 0, and greater than 0? Well, it is because those are the 3 points where they actually make a difference in the shape of the graph. So at t less than 0, I've chosen the number negative 1. So unit step function with a negative 1, it equals to 0 because it is lower than 0. Thus it is 0 subtracted by 1, and this has a negative symbol, which means that negative multiplied by negative becomes positive, so it becomes u1. So 0 minus 1 equals minus 1. And the second one is u0, because it's at equals 0, and u minus 0. And there is no such thing as minus 0. It is also u0. So 1 minus 1. Again, the value is 1 at t equal and greater than 0. And it is equal to 0. Therefore, it is 1 subtracted by 1 equals 0. And the last one is for 3 greater than 0. I chose the value 1. And as you can see, the second one, because it has this subtraction symbol, it becomes lower than 0. And therefore, it is 1 subtracted by 0 equals 1. So we can write this in a piecewise function, and it will look like this. At t lesser than 0, the value is minus 1. At t equals 0, the value is 0. And at t greater than 0, the value is 1. So to draw this in a graph, it will look simply like this. So from negative infinite to a number that is as close as possible to 0, but not at actually 0, it is at negative 1. The y-axis, the strength of the signal is at negative 1. And precisely at 0 point, the y-axis is at 0. And at a time value of greater than 0, from the closest possible number to 0 until infinite, it will be at 1. The string value is 1. So yeah, we have found the shape of the input signal and the impulse response. The next step is to convolve both of them and to find their shape. So we have found the shape of the input signal and the shape of the impulse response. Now we have to find the convolution between the two to get the output. So the convolution formula is output equals the integral of from negative infinite to infinite of the signal envelope multiplied by the impulse response subtracted by tau. And to get this, we first have to find the overlap between the impulse response and the signal input in the three time regions of the impulse response. So happen that the time regions of the impulse response that we just found are lower than 0, at 0, and greater than 0. And note, what even is tau? Well, in this problem, tau is equal to 1 if the region of the input signal involved in the formula is true to what they actually are, which means at 0, 1, and 2. In this problem, it is not 1. In this problem, tau is 0 because it is lower than 0, the range of the time. The range of the time is below 0, and input signal only exists between 0, 1, and 2. Therefore, input signal doesn't exist, and therefore the tau is equal to 0. So now, physically, there is no overlapping happening at all. So region 1 and t below 0, there is no overlap. Mathematically, we can still find the output value for the convolution below 0, at t is below 0. So again, we just put the formula here, and we have to find what is the impulse response in this formula. The t is equal to negative 1 because I just pick any random value of number. Since it is t below 0, I just pick negative 1 because it's the closest to 0 and it's the easiest to calculate it. And next to it is subtracted by 0. Again, 0 because input signal doesn't exist in this time region. Therefore, minus 1 subtracted by 0 equals to minus 1. And hello everyone, so we have found the shape of the impulse response and the input signal. So now we are trying to convolve both the input signal and the impulse response to find the graph. The formula of our convolution is always output equals the integral between negative infinite to infinite of signal amplitude multiplied by impulse response of t subtracted by tau. And we have to find the overlap between the impulse response and the input signal in the three time regions of the impulse response. In all entirety of the time regions of the impulse response, and previously we have found the three time regions are less than 0, at 0, and greater than 0. So note what even is tau? Well, in this problem, tau equals to 1 if the region of the input signal are included. If it is outside of the region, then it is 0. So yeah, first we have to do at the first region, which is at lesser than 0, and of course the input signal is not there. The input signal starts from 0 until 2. That means the tau is equal to 0. And physically there is also the overlap. As you can see, this is the input signal, this is the impulse response. There is no overlap between the two, they don't even touch at all. However, mathematically we can still find the output signal despite them not physically touching at all. So we input the formula here, the same formula, and first we have to find what is the impulse response value. So the t is equal to any number between 0, and I chose -1 because it's a simple number, and the tau is 0 because again the input signal is not included. Therefore, since the impulse signal is equal to the unit step function of t separated by unit step function of -t, therefore we put it here equals to ut separated by u minus t, and yeah, the t is -1 separated by 0, and the minus t is minus brackets -1 separated by 0, and therefore it is u minus 1 separated by u plus 1, because this is plus 1 separated by 0, which is plus 1. So the result will be 0 because this is lower than 0. Remember that the unit step function is that it is 0 when the value strength is when the time is below 0, and 1 when the time is greater than 0 or equal to 0. Therefore, u minus 1 is 0 and u plus 1 is 1. And because they are both subtracted, the result is -1. Yeah, we continue with the integration, and thus the integration is between 0 until 2, a range from 0 until 2, and we input the signal envelope, which is -2 tau plus 4, and we add the result of the impulse response, which is -1, and then we continue with the anti-derivation. And the formula for anti-derivation is basically like, it's very similar to integral. It's like this, the formula like this. Therefore, we also add it to here. The t is equal to the 2t, and the n is equal to 1, which doesn't exist here. So the variable is tau, tau, the 2 tau with exponent of 1 plus 1, because here is n plus 1 and it is 1 here. Subtracted by 1 plus 1 is 2. So 2 subtracted by 2 divided by 2 is equal to just tau squared. And for here, the constant here, it is multiplied by tau with exponent of 0 plus 1, subtracted by 0 plus 1, where it becomes 4 tau. And then remember the range from 0 to 2, we just add it here. 2 squared subtracted by 0 squared, and -4 times 2 squared subtracted by -4. Just mostly here. It's supposed to be like this. -4 subtracted by -4 with 0 squared, and it's basically just 0. It's the same with subtraction or addition. And the result is 4 subtracted by 8, and this -4. Therefore, at the range of t smaller than 0, the output strength of the signal is always equal to -4. To continue where we last stopped, we were at defining the first region. Turns out I made a mistake in explaining the first region, because the 3 regions are not based on the regions of the impulse response, rather they are based on the region of the input signal, which is at below 0, in between 0 to 2, and greater than 2. That's why for the second region, it's not at 0, rather it is at between 0 to 2. And for the convolution formula, previously we have seen that it is just this, just the integration between the lower limit to the upper limit of the input signal multiplied by the impulse response. And it turns out for this second region, we need more than just that. We need between 0 until the time of the signal, and then between the time of the signal to the maximum of the input signal range. And there is also one more. that is between the time and the time itself, which just means 0. It should be ignored. And yeah, previously we found the impulse signal through this formula. We can just assume that the time is just -1, and it is very easy to calculate. However, in this scenario, we cannot do that because it is much more complex. For example, you can derive it all the way to this step, where we find the impulse response is equal to t minus tau and minus t minus tau. However, I wrote it in my language of origin. So the tau can be any number between 0 and 2, and the t can also be any number between 0 and 2. Therefore, we cannot just subtract both of them. Therefore, to find the impulse response, we have to use a very specific rule again, the unit step function. And instead of the regular ut greater than 0 and ut lesser than 0, we use ut subtracted by tau. If it's greater and equal to 0, then it is 1. And if it is lower than 0, then it is 0. We can also infer another form of it. However, I personally suggest to ignore this rule, interpret just focus on this rule, and do the subtractions to allow for this rule to be used. And yeah, we can move to this step first before we talk about the output. So in this case, there can be 3 different scenarios. The first one is t is greater than tau. The second one is t is lesser than tau, and the third one is t is equal to tau. And these 3 scenarios correspond to the 3 possible ranges of the integral for the output equation. So, for example, if the t is greater than tau or equal to tau, then the result is 1. We derive this by picking a number where t is greater than tau, which is 2, and the tau is 1. So 2 is greater than 1. The unit step function of 1 and the unit step function of -1. The result is 1 subtracted by 0, which is 1. The second scenario is basically the same, but we reverse it. This time the tau is greater than the t. And as you can see, the result is -1. The third scenario, both of them are equal and the result is just 1. Therefore, we can infer that the impulse response of the first equation is 1, the second one is -1, and the third one is 0. If it is multiplied by 0, then it is nothing, it should not be considered. And why is it from the range of 0 to t, it is always positive 1? And why is it from the range of t to 2, it is always -1? And that seems kind of random, I would say, some would say. And the reason is because at the range of between 0 to t, it is always greater than 0. Therefore, the tau is the limit of the signal. The tau is always between 0, 1, and 2. However, the time can be greater or smaller than tau, but it cannot be smaller than 0 or greater than 2. Therefore, time will always be greater than 0. And therefore, in this case, where the time is greater than tau, it will be in this first scenario because it cannot be greater than 0. Therefore, for this scenario, we use the impulse response of +1, not -1. The same rule applies to the second one, where the maximum limit is 2. And the t cannot be any greater than the tau. Therefore, the t is always smaller than the tau in this scenario. And because the t is always smaller than the tau, we use a greater number for the tau and a smaller number for the t, which is -1. And yeah, again, for the scenario where t is equal to tau, it will just be 0. Same here, 0. So then we add both of these integrals to find the final algebraic function. In summary, again with the anti-derivative rule, where t is at the top and 0 is at the bottom, that means negative t squared subtracted by 0 plus 4t subtracted by 0 because multiplied by 0 is 0, and then 2 squared with the 2 and t squared with the 2 because because the t is multiplied is swapped with the tau, and then the 8 is from the t swapped to the 2, and then we get the same for t because the tau is swapped with the t. And the same rule applies, and we just calculate it to get the final result of the algebraic function, which is this. I cannot show it in the screen because I wrote too much. And basically, at the region of 2, which is between 0 and 2, I mean at region 2, which is at the range of between 0 and 2, the output is minus 2t squared plus 8t minus 4. And I tried drawing it, it looks like this. I didn't fully calculate it. I used some graphing tool online, and the graph would look like this. This is basically the output of the range from 0 to 2, and we need to erase this because this is not part of the range of the input signal. So again, this is region 2. If you remember closely, if I'm not mistaken, I think region 1 is minus 4. So it should be look like this. So far the graph, the final image looks like this. So now I would like to explain about the third region and BIBO stability. So this is from the last two regions. This is from the first region and this is from the second region. We are able to draw this graph apart, but we don't know what the third region will look like. To get the value output for the third region, we first have to use the convolution formula again, input the signal envelope again, and then we have to find the impulse response. And as the first region already suggests, we can find it in a much simpler way compared to the second region, simply by substituting t value that is bigger than tau. So we choose the number 3 for t, 3 for t, and 2 for tau, and 3 is bigger than 2. So for unit step function, with 3 it becomes 1 and negative 3 becomes 0 because it's lesser than 0. Thus the impulse response is 1. So we input the range of 2 until infinity because it's boundless from the output, from the ending of the input signal. And with anti-derivation, we can find that the value is 4. The value of the output in the third region. Basically, the anti-derivation makes the substitute the infinite into the tau, and then it will subtract itself with 2. And for infinite, I figured that it's quite hard to picture infinite, so I chose a large number, and I chose 10,000. So it's minus 2 substituted with 10,000 subtracted by minus 2 substituted with 10,000. And of course the result is 0 because minus 20,000 plus 20,000 is equal to 0. We just add the constant at the end, which is 4. And therefore 0 plus 4 is 4. So the output for the third region is 4. So this is the output, and this is what the sketch looks like. This is the final drawing of the convolution. And now the very last step is to determine whether or not the system is stable or not. When we say a system is stable or not, it means whether or not it fits the criteria for BIBO stability, which means bounded input and bounded output. So bounded means that it has a range from the beginning to the end for the input and output. To determine this, we have to use the BIBO formula, which is I think I should add whatever is equal to 0. 0 equal to the integral of between negative infinite to infinite of the impulse response. And now we include the impulse response, and we also use the unit step function because the impulse response has u, and u is the unit step function. So we add 3 regions. The first one is for t is less than 0. The result is 0. And it's minus 1. The result of the impulse response is minus 1. For impulse response at the second region is at t equals 0. The result is 0. And for the impulse response at the third region, the result is 1. Therefore, we sum those 3 in an integral, the integral of that formula. So the first integral is between minus infinite up to 0, is minus 1. Second one is between 0 to 0, because we again is equal 0, therefore it's the 0, just ignore 1. The third one is between 0 and infinite, and it has 1. It's 1 here, it's minus 1 here. So, yeah. The final result may seem as if it is stable because minus negative plus negative is 0. However, again, I need to remember about this symbol, which means that the number is always positive. Therefore, minus infinite plus infinite becomes plus infinite plus infinite. And therefore, the result is infinite. Therefore, the system is unstable. So, as a short recap, first of all, this is what the sketch looks like. For the first region, the value is just negative 4. It's just plain negative 4 at y equals negative 4. For the second region, it was a polynomial of 2 second polynomials, and you can reverse back if you want to see the exact equation. And for the third region, it is always 4. And if it is stable or not, the answer is no. It is not a stable. So it is not a stable system. So yeah, that's all for my video. Thank you so much for watching. I'll see you next time.